Hello and welcome to the fourth SAGIS training video. In the previous video, we learned how to create a SIMCAT file, run it, and produce outputs. In this video, we're going to learn about the many visualization tools that SAGIS has available for us to process SIMCAT outputs and visualize them. To create a DAT file, first we created a scenario. As a reminder, the name of the scenario that we created in the previous video was test_1, where we indicated the location of the DAT file, which is also the location in our computers where the outputs are going to be generated. The most common visualization tool that we will want to use after running our DAT file and producing outputs is plot outputs. We're going to select it from the SAGIS ribbon by clicking on Plot Outputs and then Plot Rivers, as we will have run the river model. A window appears where we're going to select the following. Firstly, the determinant. The determinant available to us will depend on which determinants we activated via the Global Control Settings form that was also present in the scenario settings that we were using in the previous video via the General Settings form. In our case, we have ammonia, phosphate, and BOD. I am going to select phosphate. Next, we are given the option to filter the outputs that we want to see by monitoring stations, the water body boundary, which is the endpoint of each water body that we have an output for, or Ampere, which is related to the metal permitting model that is not going to be discussed in this video. The most common option is all. We want to see the outputs for all locations at 1 kilometer intervals alongside the river reaches. Next, we're given the option to filter results that are too close to the headwater by a specific kilometer length. We're not going to select that at the moment, it's not necessary. And then finally, if our determinant has partitioning, and we have selected this, which I'm aware has not been explained yet, we could select partitioning for different determinants and therefore see different sets of results. The most common option, that is used 99% of the time, is total. And then finally we'll just press Create Map, and SAGIS will go about looking into the DAT file folder, finding the outputs, reading them, and mapping them into our model, as we can see here. It's a fairly fast process, even for large models. It shouldn't take longer than a few seconds to a few minutes for a big model. When outputs are produced via this tool, you will get a new layer in your contents map. The name of the layer is going to depend on your DAT file name, in this case test. The words GIS1, that's always going to be there. The name of the determinant, in this case phosphate, as we chose it in the window. Underscore, and then the partitioning, which is almost going to be always total, as we were saying. If we were to take a look at this layer, you'll see that we have many different fields that will contain all of the outputs that SIMCAT has produced. So for example, what we are looking at now in the map is the mean concentration, which is shown in the mean conc field. But for example, we could plot different outputs, or we could just query different output variables that the model has produced. If we zoom in, you'll see that the model is producing outputs approximately every kilometer of the river reach length, unless there is a feature in the model, such as a water quality monitoring point or a flow gauge, in which case it will produce an output at that particular location as well. SIMCAT will also produce outputs where there is a monitoring point or a plotting point location, as they're called, in the river reaches, identified by this gray circle with a dark black point in the middle. So if we wanted to visualize a different output other than the mean concentration, what we can do is go back to Plot Outputs, Plot Rivers, but this time, instead of using the top part of the window, we're going to focus on the second part called Symbology Options. Here, we're going to select the determinant layer which is any of the output layers that is automatically recognized by the form. And then we will select which options we want to see from that layer. For example, if we want to see the river flow, and we want to see the simulated river flow as opposite to the observed river flow, or the difference between simulated and observed where we have data. And in this case, if we want to see the mean, we will select those options and then click on Change Symbology. And automatically a new layer is added to the map that it's referencing the same dataset, but in this case, it has a symbology that is showing us the mean flow at the same points that we had outputs for in the past. I find this symbology particularly useful to ensure that the hydrology model is working correctly, or rather that the rich connectivity is working correctly and as expected. After running plot outputs, normally we want to run create output tables. Whilst this is not a visualization on its own, it will create a series of tables that can be used for other visualization types, in particular the pie charts, which are very common. If I open the Create Output Tables window, you'll see we have options for different tables to be created. In this tutorial, we're going to see how to create the sewage stream and work contribution tables, the output tables, and the input tables. The diffuse sector tables are only available if you are running tracking on sector diffuse, which is not considered beginner level, and we'll see in future videos. An interesting part of the form is these two drop-down menus. If I untick the inputs option, you'll see that they gray out. That's because these two drop-downs only affect the input tables. The input tables basically will track the sector point and sector diffuse contribution inputs to each water body. And if you think about it, we are adjusting those inputs using two tables, the water quality calibration table and the flow calibration table. Therefore, it's only natural that we should select those tables in here. However, that's a caveat. As you can see here, we have a water quality calibration table with an underscore WB, which stands for water body, in it as a suffix. The water quality calibration table is expressed as an adjustment factor to different determinants and sectors at a ridge scale, so you can have one different adjustment factor per ridge. However, the input data that we have is at water body scale. So we need to have a water quality calibration table at water body scale to pass to this tool. Now you might be thinking, I don't have that table, I cannot run the visualization tool. That's not correct. During the Create SIMCAT process, there is an option. If we go to that file options, this Create Water Body Calibration Tables option, if you run Create SIMCAT with this box checked, it will automatically create a version of the water body calibration table of whichever table you are passing here. When it comes to flows, the flow adjustments are also at ridge level, but that is not a problem. The Create Output Tables input option can accept the usual flow calibration table at ridge level. But in this drop down here, you need to make sure that you are passing the water quality calibration table at water body scale that you will have generated most likely using the Create SIMCAT form option that we have just taken a look at. And then finally, we got at the bottom this fraction set of options. This is generally only for metals and determinants with partitioning, and is again not considered beginner level and very rarely used, so we don't touch on that. So we simply use the total option. In this case, I'm not going to select any of the water quality calibration tables, so I'll restart the form. I'll select sewage stream and works, outputs and inputs, and press run. I'll save any edits if I've made any, and then we'll take a look at the process as it runs. This process usually creates a large number of tables. The more options you have selected, the more tables will be created, of course. It does tell you which tables have been created: test contributing sewage stream and works, test contributing outputs, output loads, monthly outputs, inputs, and so on. The tables are created for all determinants, and they will have as a prefix the name of your DAT file. Next, we will take a look inside the tables just to understand how the information has been prepared for you. Once the tool has finished running, we will see all of the tables that have been produced in our outputs file database as it is in the project setup. In this case, Saglandia file database. I have already added all of the tables that have been created to my map. As a reminder, this is contributing see what streaming works, outputs, output loads, monthly outputs, and inputs. Next, we're going to take a look at the tables one by one. I'll explain which data they contain and how it is structured. So for contributing see what streaming works, what you may find here is the contributing load from each see what streaming work to the outlet of each water body. The outlet of each water body will always be the last plotting point of a water body. If I disable the plot outputs layer, you may see this plotting point here, which is called GB water body 23 boundary. This boundary suffix that this feature has is what indicates that it is the outlet of that particular water body. And these features are essential to creating the contributing output tables. Now, if we take a look at contributing see what streaming works again, so the first row indicates that for this particular catchment, this see what streaming work called see what streaming work 4, and of course for the first determinant, which is ammonia, we'll see other records for the other determinants, such as phosphorus, is contributing this amount, 0.09 kilograms per day of ammonia, which constitutes the 100% of all the load coming from these charges at the end of that water body, and it constitutes a 0.47% of the load of ammonia currently in the river. And in this manner, we'll read all of the other records. So this table will indicate for a particular water body. For example, let's take a look at GB water body 32. We can see that there's 3 discharges contributing to the load at the outlet of that particular water body for ammonia. And this is the load. These are the percentages from each corresponding discharge and the respective percentage on the river for each one of these particular discharges. The next table is contributing outputs. Unlike contributing see what statement works, which contain contributing information in loads per day, contributing outputs, it's a concentration-based table. So as indicated by the units column, is in milligrams per liter. We can read the rows in this table as at the outlet point of this particular GB water body 3, for the determinant number 2, which is orthophosphate, in milligrams per liter, and with the following mean flow and 95th percentile flow at that particular point, the contributions to concentration are, for all the sectors, sewage 0.000115 milligrams per liter, intermittent discharges, livestock, arable, and so on. If we scroll to the right, you'll see that there is a series of fields with the suffix CUM-CON. That stands by cumulative contribution. It is important to remember that CON means contribution and not concentration, as we will see tables containing contributions in both concentrations and loads. The cumulative fields will be populated only for load-based tables, such as contributing output loads, and only if the tracking option for the diffuse sector is activated, which is not part of this series of beginner videos. If we look at the contributing output loads, the table has a very similar structure to the previous one. Scroll to the left, we'll see that again, for a particular outlet point in a catchment and a particular determinant, such as ammonia, this time in kilograms per day, again containing information on the flow mean and 95th percentile at that particular point, we can look at the contributions to the load at that particular point for each one of the water bodies and determinants. For point sources, sewage, intermittents, and so on, as well as diffuse sources, livestock, arable, and so on. And then finally, we've got contributing monthly outputs, which is the same structure as contributing outputs in the same units, milligrams per liter, a concentration-based table. The only difference is that there is an extra field called month, and it will contain the exact same data, but rather than for the monthly average, on a monthly basis, with the months ordered as usual, January, February, March, 1 to 12. We have one more table that is slightly different to the previous three. This is contributing inputs. Contributing inputs will indicate, for its determinant, the load in kilograms per day that enters its water body using the same data that we have used to build the DAT file. Unlike the other tables, which are produced only once we have run SIMCAT and therefore we have outputs, we can always create the contributing inputs table even before we run create SIMCAT and SIMCAT. The fields populated will be those corresponding to the contribution from the different sectors and also the cumulative contribution, which is already known. And this will take into account the contribution of load for specific determinants and for specific sectors to a particular water body and all of the water bodies upstream of that particular water body. We also have two extra fields, rich diffuse contribution and rich diffuse cumulative contribution. These two fields will calculate the contribution to loads for non-point sources for determinants that do not have sector data. So for example, it will be 0 for determinants with sector data such as orthophosphate. But when we work with ammonia or BOD, for which there is no sector data, it will group all of the non-point sources into the rich diffuse sector that we can see here. The output tables that we have created will now enable us to plot pie charts. The pie charts are generated using information contained into the contributing output tables or contributing input tables or any of the other tables that we have created depending on the options that we select. So to plot pie charts, we will select the visualization tool from the SAGIS ribbon. Again, we will select the chemical that we want to plot on the map. And then for rivers, we have a sub-menu of options in the advanced river options. In the tutorial with the lakes model, we'll see how to plot pie charts for lakes. In the case of rivers, if our determinant has sector data, we don't need to do anything. If we are plotting pie charts for a determinant without sector data, such as ammonia or BOD, we would select the diffuse versus point sources option, which will plot pie charts rather than showing the sector data just as diffuse or point sources. This is also a valid option for determinants with sector data if we only wish to see the contribution to concentration or loads split by point and diffuse sources rather than sectors. The plot rivers option is selected by default, and this is what we want when we are plotting river data, which is the case here. Again, plot L tracks will only be useful when we use the lakes model. And the options that we have are in-stream concentration, so the concentration in the river at the end point of each water body, and that will be plotting test contributing outputs. If we want in-stream load, we will be plotting contributing output loads. The input load would mean that we're plotting contributing inputs, and the input cumulative load will be also contributing inputs, but in this case, the cumulative contribution columns that we have seen a moment ago. In this case, I'm going to plot the in-stream concentration. If I press run, the pie chart will be generated wherever the centroids for each one of my water bodies are. So if you want to build a map and there is a centroid that's in a location where it's blocking something that you want to show, you could move the centroid away or move the pie chart away once it has been generated by editing that particular feature. Now that the pie charts have been generated, a new layer has been added to my map. The name of the layer depends on the options that I have selected. So in this case, it is that file name, test, contributing outputs, indicating the name of the table that I am plotting, in stream concentration, and phosphate to indicate the determinant. The legend for all of the sectors is also present in the layer that has been added to the map. And for example, what this is indicating is that in this particular water body, we have the majority of the concentration or contribution to mean concentration coming from intermittent sources, followed by what appears to be livestock farming, and then there seems to be a tie between the arable farming sector and sewage. Another visualization that is really useful are the river chainage plots. We've already discussed plot outputs, and plot outputs will produce a series of information, simulation outputs from the SIMCAT model at each kilometer interval, as well as at any point where there is a feature. This information sometimes can be hard to put in context. For example, contributions from these different sectors and sources by just looking at a table full of numbers. It is in this situation where the river chainage plots can become very useful. To create such a plot, we use a specific type of spreadsheet tool. So in order to create these tools, we'll go to Excel graphs, river chainage, and then we'll select the determinant that we want to visualize data for. Let's pick phosphate, for example, and the start and end reaches that we want to generate this type of cross-sectional chart information for. I'm going to select this river ridge here, for example. So as long as you know that this river ridge is one section, in this case, looking at the sim nodes might help. For example, number 12, we just click and it will pick one. And then for the next one, there seems to be a default one, but I'll just pick one on my own accord. So for example, I'll pick this one. That's probably the one that was selected. There, if we were to pick a different one, then basically that will change. Bear in mind that the connectivity needs to be valid. So for example, I wouldn't be able to pick this start reach and then this as a second reach, end reach, because it is not ending here, right? So you do need to bear in mind what is the connectivity and pick a start and end reach that are valid. Otherwise, the tool will throw an error. Once we have selected our start and end reaches, the fraction will, as we've discussed for other tools, almost always be total. We'll press run. And this will launch a geoprocess that basically has created a copy of the spreadsheet tool in your .dat file folder, as well as launched it. So it will launch automatically. Depending on the settings in your organization, it might be that you get a pop-up asking you to enable the macros, because it's a macros-enabled spreadsheet tool, or it might be that you do not get any messages. If we quickly go back to ArcGIS Pro, you'll see in this message that it's pointing you to the location of the spreadsheet, and it's always going to be in your .dat file folder. So the spreadsheet will exist in that particular location. Once you close it, you can reopen it, you can rename it. If you have different scenarios, for example, it might be worth renaming them. It will already be prefixed with the name of the scenario, but not necessarily the determinant information that it contains. So it's worth taking them out and managing them as required. Right. If we go to the spreadsheet, the first thing that we need to do is click on Initialize Data. Before we do that, Import controls will always be the first tab that you see and the only tab that you need to be concerned about. The other two tabs contain information. Data in, for example, is most of the information in plot outputs, and SAGIS inputs contains information on the input reaches and other metadata that have automatically been put in here. You do not need to modify this at all. Everything will have been populated for you already. It is possible to drive this spreadsheet tool on its own without launching it in the way that we've seen via the GeoProcess tool and SAGIS, but we will not cover that in this video, and the most common use case is simply to automatically generating it via SAGIS, as we've seen. Now, without further ado, we'll click on Initialize Data. Depending on the size of the model, this might take a little bit longer, or it will be very quick. In this case, this is a small and simple model, so it's quite speedy. In the first screen, we're going to get two charts. If you remember, we just selected start and end reach points. So in the top chart, in the x-axis, we'll get the distance from the start to the end point that we chose. In the y-axis, we'll see the concentration of the determinant that we chose, so in this case, phosphorus. The chart will show the simulated mean, which is represented in the plot outputs table using the field mean conc, but also the lower confidence limit, the upper confidence limit, the observed mean, where there is a water quality monitoring point, and therefore we've got data for them, the respective lower and upper confidence limit, and also some lake model related information that we'll see in future videos. In this case, if you remember from the map, this particular example model has artificially input a lot of load in terms of phosphorus using a feature at this point. So we are not going to see an agreement in terms of observed data. That is perfectly fine. What we should see is that at this particular point, from the start and end reaches that we selected, there is a large increase in concentration. And then every time there is a confluence and new river reaches join the main reach that we have selected, there is a dilution effect. So this is what we see here. The moment that there is a increase in the load being discharged into the river for phosphorus due to that feature that we were talking about, we register a large increase, and then every time there is a confluence, there is a noticeable dilution effect. Similarly, the bottom chart, chart number 2, shows the flow. In this case, it's showing the flow, the 95th percentile flow, which again is increased every time that we have a confluence in the river ridge structure. Now, if we click in this See Load and Compliance Charts button, what we see is a different window that automatically pops up showing two more charts. Chart number 3 with the probability of compliance. In this case, this is not correctly set up for the test model, but basically what you will see is from 0 to 100, what is the probability of compliance from your concentration for that particular determinant in the river for the different Water Framework Directive threshold bands. Again, this will only make sense if you have a real model where you have actually set up target data for that particular determinant that you're looking at. A lot more common is chart number 4, the sector concentration chainage, which is a stacked area chart showing the different sectors. I'm going to zoom in a little bit more. This chart will show you the apportionment in concentration for, in this case, phosphorus, for all of the sectors. In this particular example, what we see is, as we would expect, a lot of phosphorus coming from that one industrial feature that we have made sure to put in there, so it's obvious where the effect is happening. As there are confluences in the river ridge, what we notice is the effect of the other river ridges containing different sources of phosphorus, such as, for example, livestock and arable, which can be seen in green and yellow respectively. Now, to come back to the previous chart, we will press this C concentration charge button, and that will take us where we were before. Once we have finished studying our simulation via this particular tool, we can simply save it if required, close it, and we'll be back in ArcGIS Pro. And the next time you want to open it, just remember that it's as easy as going to the location where this spreadsheet has been generated and simply double-clicking the macros-enabled spreadsheet, and that will open it in the same state as you left it. Lastly, we are going to explain a visualization tool that it is often overlooked, and yet it is really powerful. This is Map Outputs. If we click on Map Outputs, you can see that the window is quite complex. I will now explain it step by step. Map Outputs needs, as a first input, one of the GIS layers that we have produced with the Plot Outputs, Plot Rivers visualization tool. In this case, I am going to select this one, Phosphate Total. The second thing that we're going to do is check the metric in Plot Outputs that we want to work with. And this depends on the question that we're trying to answer. So do we want to look at the percentage of the river ridge, or the length rather of river ridge in kilometers that is achieving at their target? This is only if the determinant that we have selected has indeed a target, such as it is the case, for example, of phosphate. Or perhaps we want to take a look at how many points per water body are passing or failing the target in the percentage. Or perhaps we want to look at the probability of compliance of achieving specific target, such as Water Framework Directive good. This is a metric that SIMCAT also calculates if you've input the right data. We could take a look at the model performance metric produced by SIMCAT. We could calculate what is the corresponding Water Framework Directive class, provided that we have input this data using, for example, the reach targets table that we explained in the second video on Open and Update. We could take a look at what is the concentration of each water body, the load, the percentage of contribution with regards to the concentration or the load. I'm going to provide a couple of examples. So a key point here is that the metric will tell us in these numbers next to the name which parameters we need to give the tool. So for example, if it says 2, then we need to select a parameter here. If it says 1 and 2, both from sector and output location filter. If it says 3, for example, Water Framework Directive class 2 and 3, we need to provide inputs for the output location filter and the statistic. So let's say that I want to know what is the Framework Directive class, the Water Framework Directive class, and I want to calculate this based on all points in a water body. I could do it, for example, focusing only on the endpoint in the water body, or I could do it only taking into account monitoring points. In this case, I'm going to do all points, and because I'm working with phosphorus, I'm going to select the mean, which means that it will calculate the average of the mean concentration of all the points. Say that I was working with a determinant where the metric I'm interested in is the 90th percentile. This option would tell me what is the corresponding Water Framework Directive, that is, where the calculated value falls amongst all of those thresholds, the calculated value being the median of all of the points per water body of the type that I have selected, using instead the 90th percentile value. I hope this is clear. If not, you can pause the video and go back to the beginning of the explanation. I know it is a lot of information. So now if we press apply, Automatically the tool will retrieve the necessary data and it will calculate whichever value we have requested it to calculate and will plot it on the map. So for example, what we can see here, if I deactivate the Sync Water Bodies layer, so you can see that this new polygon layer that has been generated is standing completely on its own. We're seeing that for this, again, training model, so the results are very optimistic, am I right? We can see that for all water bodies, the water framework directive is on a threshold of high, for the exception of these two, which are standing at good. Any new polygon layer, you'll notice, is created at the top of all the other polygon layers that you already have in your map. And the same can be said for point layers or line layers. They will be added to the map at the top of the respective class. As usual, the name of the new layer encodes the settings that we selected in the visualization tool that we used to create it. So this is the mapped phosphate for the water framework directive class using the mean of the concentrations for all of the points. Let's take a look at a different example. What if we want to know for phosphate and for a particular sector in this case, such as livestock farming, what is the concentration contribution using all of the points in the map? In this case, the third parameter statistic, it won't be used. It could be selecting any of the other radio buttons. It's not going to be used. Now, if I press apply, and I am also going to activate the pie charts that we have created before for comparison, this will create a very colorful map. So let's take a look at the legend for this one. This is showing us the percentage of contribution to the mean concentration for the livestock sector per water body. So for example, in water bodies where the livestock output concentration that we were showing by means of the pie charts is very high, we also expect to see this concentration as being very high. However, in other water bodies where the pie chart is showing a smaller contribution to the output concentration from that sector, we also see that this water body is showing a smaller contribution. So this is a powerful means in which we can use this visualization tool to compare and contrast data to answer specific research questions about the water quality in our catchment. We have now reached the end of the video. In this video, we've taken a look at the most relevant visualization tools that you will normally use when running SAGIS and processing SIMCAT outputs. As an exercise, I would recommend that you try running these very same visualization tools in your own DAT file outputs that we produced with the previous video. Take a look at the outputs, make sure you understand what is shown in the different tables and feature classes and layers that are added to the map. Many thanks for watching and happy modeling!